range of the function, of f of x, where f of x is equal to sine x times cosine x. Right? So this is one way for me to ask you, what's the biggest value a function can take? What's the smallest value a function can take? Using the new words we learned today. All right? So now, if we think of it this way, we just really have to study this function. And what's your name?
Michael.
Michael pointed out that there's this really nice identity that tells us sine of 2x is equal to 2 sine x cosine x. So otherwise, this is the same as the function 1/2 sine 2x. What's the biggest sine can be? 1. What's the smallest? So if we have a 1/2 in front of it, the biggest it can be is 1/2. The smallest it can be is minus 1/2. Okay? So again, I'm just trying to get you guys used to the groove and how things work here. But I wanted to point out, these aren't just words I'm using in class. I can use these to describe questions you already should know how to answer. Does that make sense? Yeah? Okay, cool. So again, we'll come back to 3. I mean, you don't actually need the extended reals. I originally had given as an example z, but I took it off. If you were going to do z, you need the extended reals. But okay, I just, so again, I said before that least upper bounds or upper bounds have as a dual lower bounds and greatest lower bounds, right? The other order though, right? So what do you think the equivalent property is for lower bounds? Well, it says that you have the greatest lower bound property if every non-empty set that's bounded below has a greatest lower bound. So let me just state a quick theorem and prove it, just so you guys can understand roughly how this all fits together. If S is an ordered set, with the least upper bound property, then maybe I shouldn't make it a new sentence because it's grammatically incorrect. S has the greatest lower bound property. So this is why I haven't actually made a big hubbub about both of them. I mean, besides the fact that they're like parallel theories, the point is having the least upper bound property is the same as having the greatest lower bound property. Okay, so what that remark I made before, you're about to see it. I'm going to prove this one for you guys. I'm going to fly solo on this, so I won't be asking for too much input. So let E not be empty. Not be empty and bounded below. And maybe I should tell you E's and S, but I'm sure you get it. Okay? So again, so we're assuming S has the least upper bound property. And I'm going to prove to you E must have a greatest lower bound. Okay? Let L be this set, and I'll tell you what this set is, or maybe I actually will ask you what this set is. So all beta in E, such that beta is less than or equal to x for all x in E. So what is this set?
Do we
Yep.
beta in S?
What? Yes. You're right. That's stupid. Yeah, it's an S. That's just a typo on my notes. Typo written by hand. Yeah, you're right. So sorry, this is all beta in S such that this is less than or equal to x. So what is this set? This is all, everyone together. Try harder next time. But yeah, it's all lower bounds of E. Right? This is the set of all lower bounds of E. Okay? Is this set? So so L, so we know, so first of all, E is bounded below. E is bounded below, so L is not empty. Right? If you're bounded below, you have a lower bound. Right? So E is not empty. So let's go over here. So we have this. Now I just have to, now what else do we know? Well, let X be an E, sorry, not E, what am I doing? L. E is bounded below, L is not empty. So let X be an E. Well, we know X is greater than or equal to beta for everything in every beta in L. Right? Because these are lower bounds. This is saying the same thing but backwards. Since everything in here is a lower bound for E, everything in E is an upper bound for L. Not too deep? Or is that like, you guys see that? If you're in L, everything in E is greater than or equal to than you. I mean, that's by definition. So any specific thing, so L is bounded above. Did I lose you guys, or should I slow down? I think you guys are lost. I see at least a couple puzzle phases. So let me just restate this. Everyone's happy with this. Since you're bounded below, there's something in L. Right, there is a lower bound. Cool. So let's just look at this time. What I'm saying is, look, we know L is the set of all lower bounds. Can you guys name an upper bound for something in L? Anything in E. Right? Does that make sense? So I grab somebody in E. These must be bigger than everything in L. So L is bounded above. Why do you think I proved this? What can I do now? I have a non-empty set that's bounded above. It has a least upper bound. See, I'm going to explain the idea of this proof at the end, so maybe it'll make more sense. Or maybe I'll do it now, actually, since everyone's puzzled. This is the idea. I have the least upper bound principle, and I want to use this to find the greatest lower bound of a set E. So what I'm going to do is take all its lower bounds and take the least upper bound of all the lower bounds. And that should be the greatest. Does that make sense? So I basically, maybe I can draw a bad picture. I'm good at bad pictures. So if this was my set E, so let's pretend it's on the real line. And then, so I'm taking all the lower bounds, which sort of looks like, I don't know. These don't mean open-ended, these are intervals. I'm just saying, so this is my set L, right? Everything less than E. I'm saying, well, the greatest lower bound of this should be the least upper bound of this. So I'm going to grab the least upper bound of L, which I can because I have the least upper bound principle, and show you it, and then show you it's the greatest lower bound. And then after this, R exists and life is good again. Everyone's happy. I gotta get the other ones. So anyways, so now that we have that, we know. So we'll let alpha be the supremum of L. Okay? And so now we have to show you this is the greatest lower bound. So what do we want to show? That alpha is in fact the infimum of E. Which means we have to show two things. We have to show it's a lower bound, and we have to show it's also anything bigger than it is not a lower bound. Right? So let's show the two things. First thing. So I'm going to first show you that this is so this is where I got to be careful because I'm about to confuse even myself. So let's let X be an, so I'm not actually going to pull these. Let's just start with some X in S, X less than alpha. All right? So we know that this X less than alpha, so this is where I'm going to use the thing. So what do we know about, what do we know about X? Since it's less than alpha, it is not an upper bound. For L. Does that make sense? So there's something in L bigger than this. Otherwise, so what you say is, there exists beta in L such that beta is bigger than X. Yeah? So what does that tell us? X is not